Today we're going to be talking about two questions on matching complexes. My name is Fran and this is Legrand.
To start, a graph is a collection of vertices and edges. Here we have a few examples at the top. To be explicit, we do not consider double edges or loops in this project. A subgraph of a graph is a subset of the vertices and edges of the graph. In particular, the third graph we have at the top here is a subgraph of the second graph. In this project, though, we rarely care about or mention isolated vertices like what appears in this subgraph. A matching of a graph is a set of edges which share no endpoints with each other. Here at the bottom in pink, we have highlighted a few matchings of this graph. A matching complex of a graph G, which we denote M of G, is the set of all matchings of a graph. We have an example of a graph and the geometric realization of its matching complex at the bottom here, where in this realization, we identify edges in G with vertices in M of G. More explicitly, we see that our highlighted pink edges 1, 3, and 5 share no endpoints in G, so the filled-in triangle 1, 3, 5 appears at right in M of G. Note that any subset of a matching is also a matching, so, as we will see in a moment, a matching complex is a type of simplicial complex.
There is a close connection between matching complexes and line graphs. In a line graph, vertices representing edges are connected if and only if the edges share an endpoint. In the matching complex, these vertices are connected if and only if the corresponding edges do not share an endpoint. This means that the one skeleton of the matching complex, only the vertices and edges, and the line graph are complements. In the example shown below, vertex 3 in the matching complex is connected to only vertex 2, but in the line graph, vertex 3 is connected to all vertices but vertex 2. In this way, line graphs have been an access point for studying matching complexes.
One part of our project has to do with 2D Buchsbaum complexes. To talk about 2D Buchsbaum complexes, we must discuss some background. A simplicial complex is a set of elements which we call faces, such that if we have an element in our set, any subset of that element is also in our set. In other words, simplicial complexes are closed under subsets. To elaborate on a previous note, with this definition in hand, it is clear that a matching complex is a simplicial complex. Given a simplicial complex delta, the link of a face rho is the set of elements in our simplicial complex such that rho union the element is in delta, and rho does not intersect the element. Thinking less formally, the link of a face tells us about the local structure of the simplicial complex around that face. A pure n-dimensional simplicial complex is one such that each face of dimension less than n is contained in a face of dimension n, and we have no faces of dimension more than n. Again, speaking loosely, a pure simplicial complex can be thought of as being created by gluing together copies of the same building block, where the blocks we can choose from are limited. Here, we see simple examples of simplicial complexes. We also see in the right that we have an example of the link of a face, namely the link of the central green vertex, which has as its link the pink edges to the left and right of it. Here, we see an example of a simplicial complex which is not pure. If it was pure, it would have to be a pure two-dimensional complex because its highest dimensional face, the filled-in triangle, has dimension 2. But the edge we see coming off this triangle is not part of a filled-in triangle. Pulling these definitions together brings us to a 2D Buchsbaum complex. A 2D Buchsbaum complex is any simplicial complex which is a pure two-dimensional complex with the additional property that the link of every vertex is a connected graph. Here we see some examples from before. At left, we do have a 2D Buchsbaum complex, while at the right we do not, because, as we noted before, the link of the central vertex is not a connected graph, even though this example is still a pure two-dimensional complex. The main goal of this side of the project has been to find all matching complexes, which are also 2D Buchsbaum complexes. In doing this, we have pursued breaking the problem down, often with good deals of casework. This flowchart outlines the general way we have gone about this, and we will refer back to it frequently. We approach the problem from the direction of finding all graphs such that their matching complex is a 2D Buchsbaum complex. In starting here, we split up all graphs into two types, those we call very connected and the others, or the not very connected graphs. To discuss these types, we need to also introduce our notion of the non-adjacent subgraph of an edge E in a graph G, which we denote n sub E, which is just as it sounds. It is the edge-induced subgraph of G containing the edges which do not intersect E. This simple lemma shows why we care to talk about this explicitly, because the matching complex of n sub E corresponds to the link of vertex E in M of G. We say a graph is very connected if n sub E is always a connected graph. Here at the bottom, we see an example of n sub E for an edge in a graph, where n sub E is composed of the pink edges on the left and right, and E is the green edge in the center. Note that n sub E here is not a connected graph, so we would say that this graph is not a very connected graph. So what is the local structure we can have in our 2D Buchsbaum matching complexes? More specifically, what can the n sub E subgraphs be whose matching complexes correspond to the links of vertices in our matching complexes? Well, if n sub E is not a connected graph, then we have relatively few possibilities, which we have all cataloged, though it gets a bit particular. Generally, we can only have n sub E be some combination of C3s or star graphs, where at the right here, we visually represent the notion of a star graph. A star graph S sub n is where we add n edges, as in the dotted edges, to a central vertex. In our image, the S sub n and C3 are the n sub E for the edge at the bottom. For not very connected graphs, we are always guaranteed at least one n sub E of this type. If n sub E is connected, we started by showing that if M of G is a 2D Buchsbaum complex, then n sub E has a path of length 4 and no paths of length 5 or more. Where by a path of length 4, we mean 4 edges strung together in a line. Knowing this, we then found all the n sub E structure when it is a connected graph. All such graphs must fall in one of these families, where we use dotted lines to indicate edges which we can add to stay in our family. So, putting these together, we describe what the link of every vertex in our simplicial complex must look like to be both a matching complex and a 2D Buchsbaum complex by looking at the matching complexes of these families. For very connected graphs, we have a fairly restrictive condition. Using this, we broke up casework in an attempt to find not just what the n sub e's must look like, but what the whole graph must look like. The global structure for very connected graphs whose matching complexes are 2D Buchsbaum complexes. The lemma shown here led to how we tackled this. We have to have at least one of the listed cycles as a subgraph. At the bottom, we see what we mean when we say cycles. Let's look more explicitly at how we use these cycle subgraphs to help find global structure. We showed that if G is a very connected graph with C4 as a subgraph and M of G is a 2D Buchsbaum complex, then either G is in the family we illustrate at the bottom, again using dotted lines to show edges we can add to stay in the family, or G has a longer cycle as a subgraph. We have very similar statements for C5 and C6, pushing casework up to higher and higher cycles. Work with C7 specifically is not quite finished, though we have passed the biggest hurdles.
We're going to switch gears now and talk about iterated matching complexes. We will define the kth matching, mk of G, to be the matching complex of the edges in mk minus 1. Specifically, to get the second matching complex, we look at only the edges and vertices in the first matching complex, and then take the matching of that graph. So in this section, we don't care about the filled-in triangles like we were talking about previously. Here is the sequence of matchings generated by C4. You can see that after 4 matchings, we get the empty set. This means that C4 dissipates, and the dissipation number is 4. If a graph does not dissipate, then its dissipation number, or d-value, is infinity. What happens when we take repeated matchings? Well, there are 3 possibilities. The first, as we have already seen, is that the graph dissipates. If the graph returns itself as its matching complex, then we say the graph stabilizes. Lastly, the graph could blow up. As we continue taking the matching, we accumulate more and more edges. There are relatively few graphs which dissipate. Here we see a table with the d-values for well-known graphs, including complete graphs, disjoint edges, cycles, and paths. You can see that once n exceeds 5 in each of these families, the graph has an infinite d-value. We will come back to the significance of the number 5 later. In general, graphs with finite d-value are not as interesting, so we will now turn our attention to graphs with d equals infinity. Snipped subgraphs have been an important tool for studying graphs which do not dissipate. First, a quotient graph is created by gluing together vertices in a graph. In G on the left, the pink vertices have been glued together to give Q on the right. In this operation, we delete edges as needed so our graph remains simple. A snipped subgraph is a quotient of a subgraph. An example is shown below. We can obtain C4 from the graph G by gluing together the pink highlighted edges. Or we could obtain C5 by gluing together the blue highlighted path of length 5. So why are snipped subgraphs useful? Well, we created the definition with the goal of preserving disconnections. Disconnections in G correlate with edges in its matching complex. Since snipped subgraphs preserve disconnections, they have the following property. If H is a snipped subgraph of G, then M of H is a subcomplex of M of G. Here at the bottom, we see the example from the last slide. You can see the edges 1 and 4 are non-adjacent in the C4, and they are still non-adjacent in G. However, edges 1 and 3 are adjacent in the C4, but non-adjacent in G. Additionally, on the right, we have the matching complex of G. We can see that the matching complex of C4 is a subcomplex of this. This is indicated by the pink highlighted edges. We will come back to snipped subgraphs momentarily. First, we need to talk about 2 special graphs. These 2, C5 and the net graph, which we will call P, were found by Agner to be the only graphs isomorphic to the complement of their line graphs. As we have discussed, the one skeleton of the matching complex, only the edges and vertices, is exactly the complement of the line graph. This means that these are the only graphs which return themselves for every matching complex. With this, we can talk about accumulation of C5 or P. If C5 is a subgraph of MK of G, then it is a subgraph of MK plus 1 of G. In other words, it cannot be lost. The same is true for P. We say that a graph G accumulates C5 or P if some matching of G has it as a subgraph. This brings us to the first of 3 interesting results. A graph G has an infinite d-value if and only if it accumulates C5 or P. To prove this theorem, we broke up the casework based on diameter. Diameter essentially gives a measure of the compactness of a graph. If you have a bigger diameter, the graph is generally more spread out. If the diameter is greater than or equal to 5, the graph must have a path of length 5. This gives C5 as a snipped subgraph, and hence C5 will be a subgraph of M of G. We then checked the diameters 1 through 4 with systematic casework, which we will elaborate on next. Lastly, diameter is only defined for connected graphs, but we know that if G is disconnected, then its first matching will be connected. So, in this way, we are able to prove the result for all graphs. The casework for diameters 1 through 4 utilize these tools. Firstly, this lemma. If G has H as a snipped subgraph, and H accumulates C5 or P, then G will as well. Then we identified these 4 graphs shown, which all accumulate C5 or P. The names, except for K23, are all of our own creation. So, in going through the casework, we looked for one of these 4 graphs, or C5 or P, as a snipped subgraph. Once we had one of these, we could say that the case satisfied the accumulation theorem. The second of the interesting results is this. If G has C5 or P as a strict subgraph, then the number of edges in the kth matching will grow without bound. The strict condition simply means that G is not C5 or P. To prove this result, we claim that if G has C5 as a strict subgraph, then it must have this G0 shown as a snipped subgraph. Then we show that the number of edges in the kth matching of G0 grows without bound, and the result for G follows. We used the same approach for the case where G has P as a strict subgraph, and claimed that it must have this G1 as a snipped subgraph. Lastly, these first 2 results give this final one in green. If G is not C5 or the net graph P, then there is no matching complex of G that returns itself. To show this, we recognize that the theorem is immediate for graphs with finite d-value, for if it was not, they would never dissipate. For graphs with d equals infinity, the blue result tells us that they must accumulate C5 or P. And the pink result tells us that once they do so, they will blow up. These together imply the result at bottom.
Thank you for listening.
We hope you enjoyed.
And here are some of our references.